We're now recording. Okay. Good morning. Today, let's talk about magnetic induction, electromagnetic induction. So let me put up the slides, I think. Now what? Here we go. Okay. All right. You can see slides, I hope?
Yeah. Yep, you're good.
Okay. Yeah. Very good. All right. So chapter 21 is about electromagnetic induction and Faraday's law. Have you discussed this in class to some extent?
Yeah, we did Monday or Wednesday.
Okay. This can get kind of confusing. And there's a lot of stuff in this chapter. So what I want to do is review the basic phenomena and then go into some of the applications that are mentioned in the homework assignment, but I won't be able to do them all because there's just too much. But the important thing is the basic phenomenon. So let's begin with a little review. So here's a current carrying wire that we saw last week. And we know that if there's a current in the straight wire like this, then the magnetic field lines make circles around like this, sort of concentric circles, depending on how far away you are. And the direction, you can determine the direction of those magnetic field lines with the right-hand rule. One version of the right-hand rule, at least. So imagine taking your right hand and grabbing the wire with your thumb in the direction of the current. And the way in which your fingers wrap around the wire tells you the direction of the magnetic field lines, as you can see in this diagram. So what happens if instead of a straight wire, you have a circle of wire? You get a magnetic field that looks like this. So I love this diagram. It's kind of neat. It's just showing you the magnetic field lines in the plane, however. And this this gray loop is supposed to be coming out of the screen. It's supposed to be perpendicular to the screen, really, but they can't draw it that way. So to determine the way the magnetic field lines go, in this case, you just apply the same right-hand rule. You just grab the wire somewhere in the direction in which the current is going. So for example, here, this diagram is showing that you can grab this part of the wire with your thumb in the direction that the current goes, and your fingers will tell you that the magnetic field in the middle of the loop points to the right, as is depicted here. Okay, does everybody understand this? Is this clear enough?
Yes.
Okay. Nobody's complaining and thank you for Kelly for playing along.
Yeah, no one's complaining.
So try this then. Suppose we have a loop that's in the plane of the screen and the current is going in a counterclockwise manner. In what direction does the magnetic field inside the loop point?
Out of the screen?
Figure that out and type something into the chat.
Julia says up.
Okay, so we have a vote for up. The question is, which way does the magnetic field inside the loop point? And we have a loop of wire, a circle of wire that's in the plane of the screen that you're looking at with a current that goes counterclockwise. So imagine grabbing any part of this wire with your thumb in the direction of the current. In which way do your fingers wrap around the wire and come out of the inside?
Out or towards us.
Yeah, is it out or is it in?
Out.
The answer is outward, yes, indeed. Can you still see me?
Yes. Yes, we can.
Okay. So I figured out that can you see the whole loop at this point? I can't see myself. I have no idea what you can see. Can you see the loop?
Cut off, but yes.
What?
The bottom part's cut off, but yes. Yeah, there you go.
Better?
Yep.
All right, so let's see. So if you're looking at me, and this current is going like this. So what I do, the current over here on this end is going up, so I grab it with my right hand and I come that way. You see that my fingers come out towards me.
Yes.
Is that a good perspective from your point of view?
Yes.
Is that compatible with what, the slides on the screen?
Yes.
Okay, good. That's good to know. All right, is that clear, everybody? Try this one. I just reversed the loop. You probably already know what the answer is, but make sure that you can work it out with your right hand. So it's the same loop of wire in the plane of the screen. Now the current is going clockwise. Inside, the magnetic field is points inward. So again, if I hold the loop up like this, you have a clockwise current. So the current is it clockwise? Yeah, clockwise. Current's going this way. And now I grab the thumb, excuse me, grab this portion of the wire with my thumb in the direction of the current. And you see my fingers point outward, that way.
Yes.
So the answer is inward, in towards the screen, right? Okay, so this is very important that you be able to figure this direction out. We're going to build on this. So if there's any question at all as to determining the direction of the magnetic field inside a loop that carries current, please ask. Here's a fact. A changing magnetic field gives rise to an electric field. Chapter 21 will phrase it this way. A changing magnetic field induces an EMF. So an EMF is kind of like a battery that's not there. It's electromotive force. It's something that gives rise to a current, just like a battery would, except that there isn't a battery there. So an electromotive force is EMF, old school term. And what I wanted to do is show you a demo here, but I don't know how to do that now. Let me see if I can do this. There's Mr. Faraday. Now, what is going to happen if I plug this in? Let's see. You still see me, right?
Yes, and then a black box.
There's a black box?
Well, I mean, in the sense of the screen is blank, but you are also in another. I don't know how to explain it. We have like two big boxes, so there's like a blank thing, and then you're also there.
Okay, but now you don't see another. No. I'm facing the screen, right?
Yes.
How do I switch the camera? Is there some way to switch? I have my other camera set up so that I could show you a demo. It's not working. Do I have an option for changing the?
Probably in your actual camera settings, you can designate.
No. That doesn't seem to be an option. Okay, that didn't work. Abandon ship.
And now you're mute.
Now can you hear me?
Yes. Yep, you're back.
Well, let's see what I can do here. Do you see I have a coil of wire? Can you see it?
Yes. Yes. Sorry, I was on mute and didn't realize it.
All right, so you see that there's a wire here, and it goes and makes a bunch of loops, and the other end of it is over here, and it's connected to these things. The wire is coated so that even though the wires are touching, they're not conducting. It's, there's a conducting core to each wire, but it's coated with something.
Dr. Barretto, it disappeared.
You don't see me?
Oh, now I do. That was weird. The camera disappeared. I don't know if it did for anyone else, but sorry.
Okay. Okay, so there you can see it, right?
Yep.
My laptop is almost closed, and I can barely see what. Do you see my galvanometer?
Yeah. Yep.
All right. So out of the galvanometer, so it's a needle here, and when there's a current that goes across these two inputs, the needle deflects. So I'm going to hook up one of these wires to one end of the wire loop here, and the other end to the other end of the wire loop. Okay, so do you see it lined up here?
Yes.
All right, now over here I have magnet on the end of a stick. This is a magnet. And I'm going to stick it into this wire, this coil of wire. So here we go. Did you see?
Yes.
Can you see the deflection in the galvanometer?
Yes.
All right. So there we go. Notice that right now, the magnet's not moving. I'm going to move it in, and I'm going to stop. So there was a current flowing through this coil of wire while that magnet was moving. Now the magnet's inside a coil, but it's not moving, and there's no current. I'm going to pull it out. You see the current goes the other way. And if I do it faster, I get more current. And if I do it slowly, slow, right? I can go in and out, and then go all the way through and come back. This is the basic phenomenon that Mr. Faraday discovered.
Cool.
It's pretty cool. Have you guys done this? Do you like do a lab where you play with this?
No. If we do, we haven't done it yet.
Okay. But look, it's real. It works. This is not just abstract. This is probably much more impressive live and in person rather than on TV, as it were. But all right, let's put this aside now. Thank you, Julia. I do agree it's kind of cool. I hope you see the coolness of it. All right, let me try to go back to the slides now. Wait.
Okay.
Do you see slides?
Yep, they're there.
Okay. All right, this is Mr. Faraday. In 1860 something or other, his picture was taken, and he was a very impressive person. He was not formally educated. He barely knew trigonometry, and he made some very, very deep and important discoveries in science. I read on Wikipedia that Einstein had pictures of 3 scientists in his office. One was Isaac Newton, of course. One was Faraday, and one was Maxwell. We'll talk more about Maxwell as we go along. Was there something in the chat?
I was just commenting that I'm in the same boat when it comes to not knowing trig, Mr. Faraday.
Yeah. Well, you're in good company because you're with Michael Faraday. So yeah, he discovered that a changing magnetic field induces an EMF. This is what we just did, right? So there's this coil of wire like this where you shove a magnet in it, and there's a deflection in the galvanometer indicating that there's a current that flows. And it goes one way, and then when you pull the magnet out, the current goes the other way, as you can see here. So how do we figure out which way the current goes? So that's one of the questions that we're going to answer. But notice that, this electromotive force, it's behaving just like a battery, except there's no battery. And so Ohm's law applies. The electromotive force is just like the voltage of the battery. So V equals IR. There's the Ohm's law with the electromotive force on the left. So that, given the resistance of the wire and the electromotive force that you generate, this is what the current is. So just like Ohm's law, just like a battery, the electromotive force comes about when this happens. Okay, so suppose we have this situation where the magnet is not moving now. So there's no movement. This magnetic field inside here is just static, and as a result, there's no current here. So there's only current when this magnet is moving up and down, and the magnetic field in here is changing. It's a little more subtle than that. And in order to describe accurately what's going on, we have to talk about magnetic flux. We've already talked about electric flux in the context of Gauss's law in the past couple chapters. Let's talk about magnetic flux. So here we have magnetic field that goes diagonally downwards, and I've just arbitrarily drawn, the book has arbitrarily drawn this area. So this area, there's nothing actually there. It's just an indication of a region of space which is square and has side L. So given its orientation, a certain amount of magnetic field goes through it, as it were. And the magnetic flux is defined as the magnitude of the component that's perpendicular to this area times that area. So you see here there's an angle between the magnetic field and this dotted line here, which is perpendicular to this area. That's the angle theta. And that's also the angle theta here. So the component of beta that's perpendicular to the area, in this case points right down into the area, is b cosine theta. Let's see this right triangle.
Yes.
So you can write it like this. Magnetic flux is BA times cosine theta. So the magnetic flux depends on what this angle is, right? The orientation of this area. It is a scalar quantity the way it's presented in the book. But it does have a direction, as you can see. It's the direction of the magnetic field. So keep in mind that the book will show you this. It'll be a scalar, but it does have a direction. The direction is the direction in which B goes through the area. All right, so because of this cosine theta, you can have no flux. In this case, there are 3 coils here that we're looking on at sort of top on, as it were. And the angle between the magnetic field and the line that's perpendicular to this cross-sectional area of these circular coils is 90 degrees. So what you're looking at is, like, here is my hoop, right? You're looking at it like this, on this end, like this. And the magnetic field goes this way. And so no magnetic field actually goes through the hoop. No flux in that case. Rotate it 45 degrees. Now we have some flux, right? The theta is 45 degrees, so we have a cosine 45 degrees in here, BA times that. And you get the most flux when the area is perpendicular to the magnetic field. And the angle is 0, and you have cosine of 0, which is 1. All right, so you can see my hoop here. No flux, some flux, maximum flux. Some flux, and then no flux again. Interrupt me if something isn't clear, please.
We're with you so far.
Okay, so now we can say what Faraday's law of induction is. The induced EMF, the induced electromagnetic force, equals the rate of change of the magnetic flux. It's expressed this way. So the capital phi with a subscript b here, that was the flux that we just defined, and then delta here is change in delta in the flux, divided by a change in time over which that change in the flux happened. So this ratio is the rate at which the magnetic flux changes. That's equal to the electromotive force, or the effective voltage, which gives rise to current that's induced. And so you see, when you have my coils of wire, and I put the magnet into it, the flux only changes when the magnetic field changed. Right? And if I changed it really quickly, I got even more current flowing because the electromotive force was bigger. Here I've just written this delta capital phi as a final minus initial. That's what change in delta is that. But we're still left with in what direction does the current flow? The way this is stated, there's this minus sign, and that's supposed to tell us the direction of the current, but it's not really very helpful. It's just there to remind you that, the way this is formulated. If you formulate this with a little bit fancier math, then this minus sign has a better meaning. But this minus sign is there to remind you something about the direction that the current flows. And how do we know? We now apply Lenz's law. This is Mr. Lenz, who was younger than Mr. Faraday but died sooner. He lived a shorter life. But anyway, Lenz's law will tell us the direction in which the current will flow. A current produced by an induced electromotive force moves in a direction so that the magnetic field created by that current, meaning the current that is induced, opposes the original change in flux. This can be very confusing. So in one situation, you have a certain amount of flux, it could be 0, through an area, a loop of wire, and then something happens to change that flux. A current will be induced in such a way to try to oppose the change in the flux. So what does that mean? Here's an illustration that we had before. So here's this loop of wire, that's the area. And here's this magnet. In this case, the magnet is a little bit farther away from below the hoop, the loop of wire, and then you move it closer. Magnetic field is stronger closer to the end of the magnet. So by moving the magnet closer, we are increasing the strength of the magnetic field inside this loop. The loop remains fixed, so the area is not changed. What happens is the strength of the magnetic field inside of it gets bigger in the upward direction, if you will. So the flux increased in the upwards direction. There will be a current that's induced in this wire to try to oppose that change. So in other words, the current that's created by this induced EMF will create a magnetic field that points downward on the inside of this circle of wire. Right? That would, if that created a magnetic field that pointed inward on the inside of this loop, that would oppose the change of flux, right? So how do you create a magnetic field on the inside of this loop that points downwards? So pull out your right hand, stick your fingers in that loop, and grab one of the wires, and you'll see that the current flows in the manner that's indicated here on the screen. So can you work that out? We have this loop of wire, so the area is not going to change. You move the magnet closer, that increases the strength of the magnetic field on the inside of the loop. Nature doesn't like that. It tries to oppose that change in the flux. It tries to do that by creating a magnetic field inside the loop that points downward, try to negate this increase in the magnetic field. To create a magnetic field that points downward, you have a current flowing in the wire in a direction given by the right-hand rule. So imagine taking the fingers of your right hand on the inside of that loop pointing downwards, grab the wire, and you'll see that the current goes in this fashion. If you grab the wire that's in front, the current will go to the left. Your thumb will be pointing that way. Does it make sense? Are people with me?
I'm with you. It sort of makes sense.
It's in the chat?
Yeah, someone said I think so.
Okay. This is excruciatingly frustrating for me because in person I could see you, and I could see whether there were light bulbs over your head that were turning on or not.
Probably more deer in headlights, but I guess for me, I think what I'm struggling with is just the wire itself doesn't change because you said it's the same area. So what about,
in this case, the wire didn't change. That's right.
So what about the current is changing? Literally just the direction in which it goes. So currently it's going downward, and now it's going to be shifting and theoretically going to the left. Or if my thumb was pointing away.
So let's sort out what's going on. By moving the magnet closer, we increase the magnetic field strength inside the circle, right? And if you calculate what the flux is, which would be the magnetic field strength times its area, the flux increased. It got stronger in the upwards direction, right?
Yes.
Okay. So nature will induce a current in the wire in order to oppose that change. To oppose that increase in the flux in the upward direction, it creates a magnetic field that points downward on the inside. It's not drawn on the screen.
Okay.
But the current will be induced to create a magnetic field that points downward on the inside of the loop to oppose the change in the flux upwards.
Okay, and because you're changing the magnetic field in the opposite direction, the current also changes.
Yeah, if you are creating a magnetic field that points downward on the inside of the loop, then the current has to flow in the direction it's indicated. And that follows by the right-hand rule.
Okay.
So if you want the magnetic field on the inside to point down, not drawn on the screen, imagine sticking your fingers inside that loop and grabbing the wire. If you grab the wire that's in front, this wire here, then you see that the thumb points to the left, and so that's the direction of the current that's induced.
Okay, I'm with you.
Let's do it the other way. Now we start out with the magnet being close, so we have a strong magnetic field pointing upwards, and then we draw the magnet away. So think about how the flux has changed. We started out with a strong magnetic flux pointing upwards. We ended up with a weak magnetic flux pointing upwards because the strength of the magnetic field got smaller. So in which way did the direction of the flux change? It changed downwards.
So the magnetic field goes up and the current goes to the right.
So the EMF is induced in such a way to create a magnetic field that points upwards. Yeah, that's right. So imagine grabbing this loop of wire with your fingers on the inside of it pointing upwards. Grab the wire that's in front, and you'll find that your thumb is pointing to the right. What's in the chat?
Julia said, yes, Kelly, okay. And Will had said partially understanding face a bit ago, but I don't know if that's changed since.
Okay. Can you guys figure out this case on the screen?
We got a now I understand, so there you go.
Okay. I'll go through it one more time for those of you who haven't answered. On the left, we have the initial situation. The magnet is close to the loop, so we have a strong magnetic field pointing upwards, and we have a lot of flux. Let's just call that a lot of flux. Then we pull the magnet away, causing the magnetic field in the middle of the loop to decrease in strength. So the flux is now still upwards, but less flux than we had originally. So the change in the flux is downwards through the middle of the loop. Nature didn't like that changed, and so it induces a current in the wire in order to create a magnetic field that points upwards to try to keep alive the strong flux that we had originally. And so in order to create a magnetic field that points upward inside the loop, stick your fingers in the loop pointing upwards, grab the wire, say the wire that's closest to the screen, and your thumb points to the right. So in this portion of the wire, the current points to the right. Loops around, goes back to the right, and then goes up here. Okay. Let's go on. How else can magnetic flux change? What we did here is we changed the strength of the magnetic field. We did not change the area of the loop. Well, you can change the area of the loop and not change the magnetic field. That's illustrated here. So here there's a magnetic field that points into the screen. See the X's? And there's a bunch of loops of wire that are held in by these hands here. And you can imagine pulling them apart, because this is just wire. And so the loop collapses and the area inside the loop becomes much smaller. And so the flux has changed. We had a lot of flux pointing into the screen originally. Now we have much less flux pointing into the screen because the area changed. The magnetic field didn't change, but the area did. Okay, so in which way is the change in the flux? We started out with a lot pointing in. We ended up with a little pointing in. So the change in the flux was pointing out of the screen. Nature will induce a current to try to oppose that change and so create a magnetic field into the screen, right, to make the situation on the right have more flux to strengthen that magnetic field. So the current is induced in the direction given by the right-hand rule. To get a magnetic field that points in, stick your fingers of your right hand towards the screen as if you were going to put them inside that loop. Grab the upper wires, and you'll see that your thumb points to the right. And so that's the direction in which the current is induced. Would you like me to say it again? Anybody?
But sure. Repeat. That is very interesting.
Okay. It is interesting, isn't it? And it's a little complicated, yeah, but nobody said that nature was simple. If nature was simple, we wouldn't be here. All right, we have magnetic field that points into the screen throughout all this region. Somebody is holding some, loops of loose wire in this circular arrangement, so there's lots of flux. The big area times this magnetic field. Then they collapse the wire by pulling on the ends. The area decreases abruptly, but the magnetic field strength didn't change. But since the area decreased, the magnetic flux decreased a lot. We had a lot of flux pointing in, and we ended up with much less flux pointing. So the change in the flux points outwards. Nature will try to oppose that change by creating a magnetic field that points inwards on the inside of the loop. If that were there, that would increase the flux, right? So in order to create a magnetic field that points inward on the loop, you need a current as indicated, and that's consistent with the right-hand rule. Imagine sticking your fingers of your right hand inside that loop and grabbing, say, the upper wires. Your thumb points to the right, and so the current goes to the right. You could also stick your fingers in the loop and grab the lower wire, in which case your thumb would point to the left. Right? So the current would end up going in a clockwise manner. Okay? Here's another way that you can do it. There's this dotted region where there's a magnetic field that points out. See the circles with a point in the middle? That's the point of the arrow pointing out at you. And then here's a loop of wire. You could just take the loop of wire and move it to the right to a region where there's no magnetic field. So this is pulling a round loop to the right out of a magnetic field which points out of the page. So if you do that, figure out in which direction the current in the loop is induced.
Can you repeat that one more time? I'm sorry.
Anybody got it? Got to use your right-hand rules. And I could see if you were actually doing it if we were in person, and see if you're actually doing it. I hope you're actually doing it. All right, let's walk through it in the interest of time. We start out with a lot of flux pointing outwards. If you pull the thing to the right, we have less magnetic field inside of the area, so the flux decreases. It still points outward, but it decreases. So that means the change in the flux was pointing inwards. To oppose that, nature will induce a current in the wire, creating a magnetic field that points outwards to try to recreate the lots of flux that we had originally. Okay, so in that, we want a magnetic field induced by a current that points outward. We stick our fingers through the loop from the back outward towards you. Grab one of the wires, say the wire on the right, and your thumb should be pointing up. In that case, we have a current that is induced in a clockwise manner. On the right, it points up. So we get a counterclockwise, as I was indicating with the letter. A counterclockwise current. Does it make sense?
Yes. I don't understand yet the right-hand rule here. So I'm
okay.
sorry, I don't know how to ask that.
We started out with a lot of flux pointing outwards, move this thing to the right, and then we have less flux pointing outwards. So the change in the flux was inwards. To oppose that, nature creates a magnetic field that points outward on the inside of the loop, and that's created by a current that's induced in the wire. To figure out the direction of the current, remember that we want to have a magnetic field that points outward on the inside of the loop. So take your right hand, reach behind the screen, and stick them out of the screen on the inside of this loop. I know you can't do that, but imagine doing that. And then grab the wire. If you grab the wire on this end, you'll find that your thumb is pointing upwards. What's in the screen? What's on the chat?
She said, "Oh, okay, I see. Thank you." And then I just explained that you had to follow your fingers first and then look at where.
Kelly, you're breaking up. I don't know what you're saying. Can you say again?
She just said, "Okay, I see you," and then I also said the same thing in words. So.
Yeah, you're breaking up, so I don't really know what you said.
We're good.
I'm gonna go and check myself what the chat says. We're good. Okay. I'll just go with you're good because we're out of time and I've barely gotten to my slides. This is terrible. Oops. All right. So this is in the book. Of course, it's much better if someone explains and answers your questions. But go through the other parts. Here's a loop that's rotating in this manner with a magnetic field that's constant one way, and see the flux changes. So figure out which way the current goes with only a rotation of less than 90 degrees. And then this is the list of things that I have left to talk about in the remaining, 14 minutes? It's like a lot of stuff. But let's go through it. This is the stuff that's relevant to the homework. These are the subjects. That's why I picked them. I looked at what's in the homework. This is what it's about. Solenoids. This is actually from the previous chapter, which I didn't get to talk about last time. But all right, we already saw this picture that if you have a single loop of wire with current going through it, you get a magnetic field that looks like this. Well, you could have multiple loops of wire to make the magnetic field on the inside of the loop stronger. And this is called a solenoid. So you make a bunch of loops like this and you run a current through it and you create this magnetic field. An electromagnet, right? Maybe you did this in elementary school, I hope. Okay. If you have a loop like this that has length L with n loops, then this is a formula for the strength of the magnetic field on the inside. This you can get from Ampere's law, which we didn't have time to talk about last week. This is the end result. Mu 0 is that special number. The n is the number of turns of wire that you have. And L is the length of the solenoid. Okay, so this is a nice formula. Turning it around, you could have this, well, it's the same kind of sort of thing. Here's a bunch of loops like this. And suppose that, turning it around, suppose that instead of putting a current into the wire to create the magnetic field, instead you have the magnetic flux changing on the inside to induce a current. That's the example that we've done before. And Faraday's law tells us the rate of change of the flux is equal to the electromotive force. But if you have more than one loop in which the flux is changing, you multiply by the number of loops. So before, remember, we had basically just one loop of wire, and so this n wasn't there. With a bunch of loops, we see that the n really was there. It was just a 1. If you have many loops, then you just put the number of loops there. That's pretty, because with the same rate of change of flux, you get n times as much electromotive force, and so a lot more current can flow that way. And then there's this idea of mutual induction. So you could have one coil, here the one on the left, through which you put a current. Coil number 1, you put a current in and therefore create this magnetic field. Coil 2 is just passive there, but the magnetic field on the inside of it starts to grow because of the current that flows in coil 1. As a result, there's a current that's induced in coil number 2. So you see the idea of mutual induction. Coil 1 creates a magnetic field, and so creates a change in the flux on the inside of coil 2, and therefore induces a current inside of coil 2. Right? That's what it says over here. If there's a change in current I1 that induces a changing magnetic flux in coil 1, that flux spills over in coil 2. So the magnetic flux in coil 2 changes, thus inducing an EMF in coil 2. Do you guys have cell phones or smart watches that you charge by putting them on a plate? This is how that works. The plate is like coil 1. There's coils in there, and there's a wire there's a current that goes in there. It's probably an alternating current that goes back and forth. So that's creating and destroying a magnetic field, and then putting a magnetic field the other direction, destroying it, and going back and forth. Therefore, when you put your smartwatch on it, it has some coils that are just passively there, but the magnetic field that grows and shrinks spills over into the inside of the coil inside your watch or smartphone or whatever it is you're charging. And because the flux inside those coils is changing, current is induced, and that can go and charge the battery. This is also how an induction stove works. Right? The stove has coil 1 in it, and coil 2 is basically your metal pot that you stick on top of it. The flux changes, you have currents going through it, there's a big resistance, and so it gets hot. This is kind of the way that Faraday was doing it. He has this iron core, and the wires are over here. What the iron core does is it keeps the magnetic field enclosed within it, basically. So close this switch, current flows, you create a magnetic field, it flows over into here, and the magnetic field inside of this coil Y grows, and you induce a current. The way it's set up here, here's a battery. So if you close the switch, you'll get a transient current on the right, and just stop, because once this current is constant, we have a certain strength of magnetic field which no longer changes. And if the magnetic field is not changing, the magnetic flux is not changing, and there's no more induced current. So this is more interesting if you have an alternating current. If the current is alternating, the magnetic field inside grows and shrinks and grows and shrinks and grows and shrinks. The magnetic field is constantly changing. And so you're constantly inducing the current on the right. This is one of the reasons that we have AC current running to our houses, because we can do this sort of thing. Can't do this with DC. So we have now the idea of transformers. Not this kind of transformer. Yuck, yuck, yuck. Bad joke, I know. This kind of transformer. So this is like the brick that's hooked up to the middle of the power cord to your laptop. That's changing that's transforming the voltage that comes out of the wall into the voltage your laptop needs. Or sometimes the transformer is directly on the plug, as you can see here. In fact, this one changes the input 120 volts from the wall into an output of 5 volts. And actually, you can see that it changes from alternating current to DC, because USB is DC. But never mind that detail. This is basically what a transformer is. It's kind of the picture that I just showed you here, with different numbers of wrappings of the wire. So on the left, there's the primary. This is basically the current going in and creating a magnetic field in here. What this green thing is basically a chunk of iron, which will contain the magnetic field that's created. So the current goes in on the primary side. It goes through these loops and creates this magnetic field. And it's an alternating current, so that the magnetic field is created and destroyed, and created and destroyed, and created and destroyed. VP you could think of as the RMS voltage of that AC current. This iron rectangle thing maintains within it the magnetic field that's created on the primary side, and moves it over to where the secondary coil is. And this wire is just passive until there's that changing flux on the inside of it. Notice that there are a different number of turns, right? NS turns on the right, S for secondary, and NP turns on the left, P for primary. So we have the same change in flux, because the magnetic field is doing the same thing, the area is the same, but we have a different number of loops. This is what I just said. The change in flux is the same in the primary and the secondary coils. In the primary side, we have this relationship. And you can think of it as putting in the voltage and creating this change of flux. On the other side, we have the same equation except with subscript S. And you can think of it as the changing flux is now creating the voltage Vs. For alternating current, again, you can think of Vp and Vs as RMS values. All right? Now, if you just divide one equation by the other, this flux, this change in flux, rate of change of flux cancels out, and you just get this. And so take this side of the equation, divide it by that one, Vp over Vs. On the other side, this side of the equation divided by that one, the minus signs cancel out, the delta phi over delta t cancels out, and you get this equation. So this tells us that we can change the voltage from the primary value to the secondary value by having a different ratio of turns. Let me skip over this. If you have an ideal transformer, you can now make a relationship between the currents that are involved and the number of turns. Keep these subscripts straight. In this equality, you have the subscripts PP on both on the numerator, and if you want to equate it to the currents, then they split, right? You can see. Okay, so this is how a transformer works. Again, this is an easy way to change a voltage from one to another, and this is the main reason that we have AC currents in our wires, because you can deliver lots of power at a high voltage, and that's much more efficient than doing it at a lower voltage. And in order to change the voltages, you need a transformer like this. And it's easy to do with alternating current and very hard to do with direct currents. Before I go on, I remember that I need to note the attendance. So let me do that. I'm gonna take snapshots of who is here. In the meantime, if you have any questions, please formulate them, type them into the chat. And as I suspected, we have very little time left for what I wanted to do. But I'll post the slides, of course, all the slides. Review them later if you wish. Okay, I have the attendance notated here. No other questions in the slides? I mean, in the chat? No? What does it say?
I just said a way to remember the order of the subscripts is you could do VPN, so VP will always go with N for the top. And then the bottom, well, it's just not VPN.
Okay, because there's eyes, yeah. If that works for you, sure. I've got what? I've got like 2 minutes. Let me just say the next thing. Inductors. So an inductor is a coil of wire like this. And you can write down a relationship between the rate of change of the current and the induced EMF. I mean, we know that if we put in the current, we're going to induce a change in the EMF. Excuse me, a change in the flux and such. So there's this self-inductance. And this is the relationship. On the right is the rate of change of the current. On the left is the induced EMF in that same wire, so it's a self-inductance. And this L is a number called the inductance of this coil. It has to do with the geometry of it, how many turns there are, the area, etc. But this is a useful relationship that shows up in the homework. The units are henries, which are defined like that. And since I have just a couple of seconds left, I'm going to skip ahead to this and just make the final comment. You can make a circuit that has, as you can see on the screen here, a resistor, a capacitor, and an inductor. I didn't have a battery in here, but if you can imagine that there is some current flowing, the current will cause an accumulation of charge on the capacitor, and then the current will stop. And then this charge will cause the current to flow in the opposite direction. Right? So some charge will accumulate on here, and then it'll start to flow back. Now, when the current goes through the inductor, it starts to build up a magnetic field. And remember, it doesn't like to change that. So when it starts to build up, it effectively has a resistance, and so the current goes down. Once the current has built up, when the current starts to die down, this inductor doesn't like that flux to change, and so it prevents the current from decreasing. The end result is that you have a sloshing back and forth of current in a circuit like this. And the frequency at which it sloshes back and forth is determined by the resistance, the inductance, and the capacitance. This is a radio. And you can tune the radio to the frequency that you want to listen to, a radio station, by changing these things. Right? So the radio waves come through into the circuit and induce some current, and it resonates if it happens to match with the natural resonance of this circuit. I'm out of time. I have to stop. Lots more to have been said. I'm going to post some questions that I have answers to handwritten, which I never get to discuss. But since I'm out of time, I have to stop. So we're done. Have a good day. I hope this was useful in some way, even though it was kind of rushed. See you later, everybody. Have a good weekend. I'll have it tomorrow. I'll post the link in the hour.
Okay.
Later today.
That was going to be my question.
Okay. I hope it was helpful.
Always. Thank you. I have to go to class.
Hey, guys. You're welcome, Julia. Your questions are always welcome because they indicate that A, someone's paying attention, and B, it helps me get the message across better. So thank you for your questions. Okay, see you tomorrow. See you tomorrow. Excuse me. Oh, I'm going to stop the recording.